Audio, testing, testing. Thanks, YouTube, beautiful mind here, and we're continuing our, let's go like this. Exploration of chapter 3 on applications of differentiation. And so here we're going to be looking at section 3.5, optimization in business, economic, and general applications. The main objective here is that we'd like to solve optimization using max and min problems using calculus. Solving max-min problems, read the problem carefully. If relevant, make a drawing. Make a list of appropriate variables and constants, noting what varies and what stays fixed and what units are used. Label the measurements on your drawings if one exists. To an equation involving a quantity Q to be maximized or minimized. Q in terms of the variables of step 2. Try to express Q as a function of one variable. Use the procedures developed in sections 2.1 to 2.3 to determine the max or min values and the points at which they occur. We have this example. It says from a thin piece of cardboard, 8 inches by 8 inches, square corners are cut out so that the sides can be folded up to make a box. What dimensions will yield a box of maximum volumes? And then what's the maximum volume, right? So it says from a thin piece of cardboard, 8 inches. So we're starting with the square, right? I'm going to use this color since we're cardboard. It says, so copy. I'm just being a little bit extra for some reason. So we have this says a thin piece of cardboard, 8 by 8, square corners are cut out so that the sides can be folded up to make a box. Okay. Let's do. So we're cutting out, and we can mark it. We're cutting these out. Like we're removing this guy. This, let's not do that. Cardboard square corners are cut out such that they can be folded up to make a box. What? So we're cutting some. These are going to be some unknown amounts, right? So we're cutting. This is X. This is X. All of these short pieces here are X's, right? The same distance because it's supposed to be a square. So then when we're done, we're going to finish with something of the following nature. We can copy and paste. And just to give it that 3D effect, we're going to do a partial erasure. That's we want to cut it here. I think that's it, right? So then when we're done, we're going to fold flats up and we'll finish with the box like this. So then if we want to label these different parts, long part, so then the remaining side here, 2x. So this side should be from here to here. And here. This is also 8 minus 2x from here to this is the setup of what's going on. Okay. So it says from a thin piece of cardboard, where corners are cut so that the sides can be folded up to make a box. What dimensions will yield a box of maximum volume? All right. So we want to identify, we want to maximize the volume. Right? Volume. Question, right? This is going to be what? The length times the width times the height, and the height from here to here is x. An expression for our volume times width times height. So in this case, that's going to be the 8 minus 2x squared, because you multiply it by itself twice, and then we're going to say times x. We want to find the maximum volume. This, we need to look at the first derivative, right? Let's expand this out a little bit further. Like for instance, if we FOIL there, x plus 4x squared, and then all of that times x. And so then our volume in expanded form is going to be 4x cubed minus 32x squared. Right? Maximize this. If we want to maximize this, we need to look at v prime, or take the derivative and find the critical values. So then 12x squared minus 64x plus 64. We want to set this equal to 0 and solve to find our critical values. Let me see, 12 times 5, you can divide by what, 4? Let's divide everything by 2. So then we'll get 6x squared minus 32x plus 32 equals 0. But thing by 2 again, we'll get 3x squared minus, what is it, 16x plus 16 equals 0. So then we want to solve this. I use this technique called the AC method of factoring. 3 times 16 is what? 30 plus 18 is 48. For two numbers that multiply to give us 48 and add to give us negative 16, I'm gonna just go through all the factors, right? 8 also is what? 6 times 8? Times 2 times 2, and 6 is 2 times 3, right? So I'm just go through all the combinations until I get to 16, right? And the way we do it, so the first is like 1 and 48, but that adds up to 49, so these are not the 2. We can do 2. So if we use this 2, we have what? 8 times 3, we have 24 left over. 6, so these are not the 2 we're looking for. We can do 3 because we have this 3 right here. 3 times, now if we use this 3, all right, to 19, so these are not the 2 numbers that we're looking for. We can do 4. See how I'm just going on the left, I'm going 1, 2, 3, 4, finding the corresponding product. So if we use 4, that means these 2 have been used. We have what, 12 left over. And notice that 12 plus 4 is 16, but we want negative 16. So then all we do, negative 4 and negative 12. These are the 2 numbers that we were looking for, all right? So what we're gonna do to factor this guy, we're gonna rewrite this middle term using those 2 numbers that we just found. And then I think I'm going to use, I like this box method that my students gave me. I'll share with you. So we're going to rewrite that negative 16. Negative 16x using those 2 numbers that we just found. So then we get the following. 3x squared minus 4x minus 12x equals 0. Okay. Okay, so I'm gonna do this box, right? This is fine, and we can keep going with this, but I want to go back to the box techniques, right? So now, we're ready for the box technique. So then I'll just use this color. It's like this. Now that we found the two numbers, in the upper left-hand corner goes the original, or goes the leading term, which is this 3x squared. The bottom right is the constant, which is at 16. And then the diagonal, we rewrite that negative 16 using the two numbers that we just found. So we're going to put negative 4x and negative 12x, right? So now when we go to factor, if we look at the two on the top, right, what's their greatest common factor? It looks like they both have x. So it looks like we can factor out an x from both of those. If we look at the two on the bottom, what's the greatest common factor? It looks like it's 4x. Let me think about that. Negative 4x. Sorry, just negative 4. 4. On the left, they both have x and 3, so we can factor out a 3x for both of those. I'm going to do another negative 4, right? So then our claim, let's start back here. Let's get a copy of this guy. Copy. This factors into this 4 and x minus 1. And we just want to FOIL really quickly just to check and make sure that it works properly. So first times first gives us our 3x squared. Outer times the outer is negative 12 minus 4 is negative 16. So those check out. And then negative 4 times negative 4 is a positive 16. Okay. So with all of this, so we just found the critical numbers right now, right? We get that what? The critical numbers are x equals 3 or positive 4, right? These are the candidates. Let me see. And since we're working with volume, we can't have a negative volume, so we're going from like 0 to infinity. We should test to make sure that these are like max or min values. If we put these on the number line, here, and here's 4, right? And we want to see so let's look at f prime. 0. This is probably crooked. It feels crooked. It's on.
2 lights.
Setting. 4/3 is 1 1/3. So to the left of 4/3 will be something like 0. If we plug in 0 into the derivative, we get a positive result. If it's positive over here, so that means our original function is increasing. 4/3, that's a 0. So that's going to be a 0 in the derivative. That's 1 1/3, so we could choose something like 2. If we put 2 in the first derivative, this is positive, this is negative. So then the first derivative is negative here. So that means the original should be decreasing. Again, this should be 0 in the first derivative. And then to the right of 4, we could test something like 5. This is positive, this is positive. So the first derivative is positive here, which means our original function is increasing. Okay, so now if we want to maximize the volume, so our local max is going to occur when x is 4/3, and we just need to find the corresponding y. Right? You know, so my y equals, we got this 4x to the power of 3 x squared corresponding y. So I'm going to go to variables, call on that function I just typed in. What's the corresponding y when x is 4/3? It's a fraction, just in case we can express it as a fraction. For 27, can I just hit enter? I want that as a decimal. $7.9. Okay. So what are the dimensions? Okay. So now maximum, so we'll just call this star. We got a max volume of, hey Google, turn the lights on. We're gonna call it 37.93 cubed. Is thirds, right? So then we want two times 4/3. So 5 1/3 by 5 1/3 by 4/3. So the dimensions, it's inches by 5 1/3 inches by 4/3 inches. And these dimensions maximize the box, produce a max volume of 37.93 cubic inches with these dimensions. Okay. Let's see how do we do. All right, we got these results. Hopefully we kept our mistakes to a minimum to non-existent. Sometimes, I mean, obviously I still make mistakes. And then I feel like it's not about not making mistakes, it's about learning how to adjust and catch them and recover from them. All right. So 5 1/3 by 5 1/3 by 4/3 to produce a max volume of 37.93 cubic inches. Okay, let's see. I think we got an image like this. We got the 8 minus 2x. Okay. Did we get that? I think we got the same thing. Uh-oh. I forget that. Let's go back. No, we got 4x cubed. 4. That's fine. Critical value on 0 to 4. So now we find the second derivative. So they did their something different because they would identify the interval over which, for instance, x, they couldn't go beyond 4 inches. So then once they got the 4/3, they got the one critical value on the interval. So then they use the second derivative. They got that the second derivative was negative when they plugged in the 4/3, which means we should have a maximum value. Cubic, I think that's what we got. Okay, so they didn't explicitly find each, they just found the x, right? cut out away from each corner, and the maximum volume is this. I think we got the same thing. Okay. That was an adventure. I leave the quick checks as an exercise for you. If you would like to. It says a stereo manufacturer determines that in order to sell X units of a new stereo, the price per unit in dollars must be this. The manufacturer also determines that the total cost of producing X units is given by this. Find the total revenue, and then we have these other charges. So the total revenue, the revenue is going to be what the money generated. So in this P of X is the money generated from selling one unit. So then the total revenue is going to be X times P of X. All right. I think we have enough space to write it here. R of X, if we say X times P of X, it's going to be 1x minus X squared, right? It is what? Revenue minus cost? The function we just found minus the cost function. Minus the cost, right? So let's go get a negative X squared. Minus 2 is what, 998? 8x. Of X minus C of X to get P of X. Profit is revenue minus cost. I just didn't write it down. So then it says for part C, how many units must the company produce and sell in order to maximize the profit? So if we want to maximize this guy, we need to, now we got to like take notes. We need to look at the derivative. So if the derivative equal to 0, okay. Profit function. So we got a P of X. We got this negative X squared plus 998X minus 3,000. Okay. We want to maximize the profit. So let's look at the first derivative. So then the 2 comes down, we get negative 2x plus 998. Okay. We want to set this equal to 0 and solve. So then x equals, that's a 918, that's 9, 499. Profit, let me see, lowest would be what? I mean, it could go negative, but we want to go from like 0. Let me think. I'm just a fan of, comparing this, use it the first derivative and compare on either side. Nine. I'm just going to look at the first derivative. I guess since it's the only critical value, we can look at the second, we can use the second derivative. Real quick. So we got a P prime, so let's look at P double prime. -2. P double prime of 499. Right, what means, so the second derivative is negative. That means our original function is concave down, which means that this is the max. So we have a max value. So the max profit, let's just call it profit because that's what we're talking about. The max profit so we plug in at 499 to the original. negative x squared plus 98x again when x is 499. Oops. Max profit of $6,001 when we produce and sell 499 units. Kind of play with it a little bit to verify, like if we choose, if say we produce less or more, like anything else that we produce should less of a profit, right? So and it's correct. For instance, say we did, let's do 500. If we did 500, our profit should be less than 6,000. Let's say we're missing out on $1, right? Let's try 505. So we produce more, right? No, all right, okay. And then say we produce less than 499, like let's do 498. So anything other than the 499 is producing less profit, right? So we're able to maximize the profit when we produce and sell 499 units, and the max profit will be up to 246. Okay. So then, what price per unit must be charged in order to make this? What price per unit? Units produced and sold. Let me see. We got a max profit of 246,000. How many units must they produce in order to maximize? We got 499. What is the max profit? And then what price per unit must be charged? This profit. So basically they want us to solve for the little p of x. So then the profit function was r of x I think we just take that profit and we divide by the 499, right? So we say that 246 divided by 499, and that will tell us the price per unit. 246,001 divided by 499. That's right. So we'll say the little p of x, price per unit. $2, we're going to say 99 cents to maximize profit. Okay, let's see how do we do. That was interesting. Can I just paste? Nope. And paste. Okay, let's see how do we do. We're going to compare this to our prepared notes, all right? Let me was the quantity times the price, so X times P. The profit was the total revenue minus the total cost. I think we up 980. Okay, see, there's a typo. Ours, it definitely said that the cost, we had a 2X and theirs is 20, so that's not our fault. Oh, that's irritating. I feel like going back to redo all that. I'm not going to redo all that. I'm just going to note it here. Hey, this is a typo. EX, right? And that throws everything off from the beginning. So we would have to go back, profit instead of 98, that would be use of prepared notes, but that was a typo. I didn't even know that was like that. So that means all of this stuff was going to be off. Get the 980, that's fine, but as long as the concept is there, that's the main idea. So then the derivative, we have 499 because that 0 was missing. Since there's only one critical value, they got the negative, the 490. In our case, it was the 499 uses the max. Okay, that's fine. The max given by that much, that's fine. Thus, the stereo manufacturer makes a maximum profit of this when 490 units are bought and sold. The price per unit, oh, okay, it's 490. So that part we did wrong. P of X, basically you plug in, that tells you the price per unit. So if you have 490 units, you plug it in, that means, you know, so we did need to make an adjustment there, but you know, it's okay. So, you know, you're living alone. Okay. But yeah, the original was missing a 0. So it threw off, you know, it was trying to waste our energy and time. Usually I use the quick checks. I leave those as an exercise for you. Okay, so I'm not going to do that right this second. But again, if you ever want to work through any of these, we can talk about it and work through it together. Also, I'm kind of faded. So, but we got like 2 more examples that we'd like to do, but I'm totally like spent. So now this example, we have life science, concentration of a drug in the bloodstream. A drug is administered into the bloodstream of a patient. Let C of T represent the concentration, C of T in nanograms per milliliter, okay, of the drug T minutes after it's administered. What is the peak concentration of the drug in the bloodstream and when does the peak occur? So basically we want to maximize this. If we have this function, if we look at the first derivative, find our critical values, and then, you know, basically just do what we've been doing, you know, and we can answer those questions. So then let's look at the first derivative. So C prime of T. Looks like we have to use the product rule here. So we say the first, which is this guy. Second, so the derivative of E is itself. Of the exponent, my headphones are dying. Let me put in this other one. Times the derivative of the exponent. So that's going to be 0.04. So that's the first times the derivative of the second plus the second. The derivative first is just going to be 25, and it's a repeat. Everything is repeated except for the t. So 25 e to the negative 0.04 t. Okay. So then we want to do our best to set this to 0. Now it looks like both terms have 25 e to the blah 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 blah. Let's factor that out. And again, we want to set this. We're going to need equal to 0, and I'm going to go ahead and factor. We can factor out the e to the negative 0.04 t. And when we do this, the first one, it looks like we're left with negative 0.04 t. Equals 0. So now, when will this be 0? If we use a 0 factor property, we set each factor to 0 and solve. If you set this guy equal to 0, I don't think there's a value of t that's going to make this 0. So we're not going to get a 0 from there, but we can get a 0 from here. If you set this to 0 and solve 0.04, t equals 1 divided by 0.04 for 100, so 25. There's one critical value. We can use the second derivative. Let me see. Is it worth it to do? Yeah. The second derivative. times the root of the second plus the second times the root of the first. That might be a bit much. First times the root of the second. It's going to be a negative value plus the second. So if we look at the second root, to see double prime of t, we got to use the product rule. So the first, which is this guy, 25 e to the negative 0.04 t. First, second is just going to be negative 0.04. So that's the first times the root of the second plus the second, which is this. First, okay. E to the negative 0.04 t times the root of the exponent. 0.04. On one line so we can be more clear. Let me see if we can. We want to evaluate if we plug 25 in. Or negative, right? Okay, I'm not going to crunch the numbers. I'm just going to use some shorthand, right? If we plug 25 minutes in, this term, this is going to be hopefully my headphones are okay now. So that's 4 over 100 times 25. So 4 times 25 is 100. So that's what? A negative 1, so that's 0. So it looks like all of the right-hand side is gone. Okay. So it looks like all of this gets knocked out by that. This all collapses to 0, right? So that's a 0. That's negative. That's, what we say? That's a negative 1. And that's positive. So that's negative, right? So long story short, our second derivative is less than 0, which means our original function is concave down, right? So that means that this should be a max value, right? So then C of t, okay, I think we got it. So then C of t is max, or has a max value. The concentration has a maximum concentration of, now basically we plug in 25 into the original. I'm just going to use my calculator at this point. Y equals, clear, 25, hopefully I didn't make any mistakes, x times e to the power of negative 0.04x. Okay. And then we want to evaluate this when x is 25. So approximately 230 nanograms per milliliter. So the concentration has a maximum concentration of 230 nanograms per milliliter at 25 minutes. Okay, let's just go like this. Start it again. Okay. Okay. So we have a max concentration of approximately 230 nanograms per milliliter at 25 minutes. Let's see. First, find the critical values, factoring. So then they get 25, right? So it's a critical value. Evaluating C at 25, we get, yeah, we got 230, that's fine. They didn't look at the second derivative to verify, but that's fine. Oh, okay, there it is. Using the second derivative, they got that. Yeah, they got a negative, right? Okay. So then since C double prime of 25 is negative, the graph is concave down. So 25, 229.92 is a local maximum point. The drug reaches this high concentration of 229.92 nanograms per milliliter 25 minutes after it's administered. So the concentration is peak at 25 minutes, and then it starts to taper from there. Okay, I think we have one more example that we're gonna get through. So we have this theorem 10. It says the max profit occurs at those x values for which r prime is equal to c prime and r double prime is less than c double prime. Okay. So promoters of international fundraising concerts must walk a fine line between profit and loss, especially when determining the price to charge for administered to closed circuit TV showings and local theaters. By keeping records, a theater determines that at an admission price of $26, it averages 1,000 people in attendance. For every drop in price of $1, it gains 50 customers. Each customer spends an average of $4 on concessions. What admission price should the theater charge in order to maximize the total revenue? I'm totally spent. So let X be the number of dollars by which the price of 26 be decreased by. If X is negative, the price should be increased, correct? So the revenue is going to be the revenue from the tickets plus the revenue from the concessions, right? So the money generated from tickets. So if you think about the money generated from tickets, you have the number of people times the price per ticket. And then the revenue from concessions is going to be the number of people, I think, let me see before. It says each person spends an average of $4 on concessions, right? So we have our revenue function, the total money generated. Let me see. Maximize the revenue. So we have this revenue function. I think that's it. So then to maximize it, you look at R prime, right? You take the derivative. You get X equals 5. So since there's only one critical value, we can use the second derivative. So the second derivative should be negative in this case. So it's going to maximize it. So that confirms that it's a max value. Okay. That's X equals 5. So this theater should charge 26 minus $5 is $21 per ticket. Again, I just used that because I'm totally spent. I usually leave these as an exercise for you. And in a summary, it says in many real life applications, we wish to determine the minimum or maximum value of some function modeling a situation. Identify a realistic interval for the domain of the input variable. If it is a closed interval, its endpoint should be considered as possible critical values. Maximum profit occurs at those x values which r prime is equal to C prime and R double prime is less than C double prime, where R of X is the total revenue and C of X is the total cost when X units are produced and sold. Okay. So on that note, we're going to end the session here. We can talk about any of this stuff. Just let me know. We're going to end the session here, and from one beautiful mind to another, enjoy the rest of your day. Okay, guys, take care. Peace.